Christian Medina, and I'll be doing a video about linear programming. Today, we will be calculating the min and max from a function. We will be doing this by forming our own functions from word problems. And by graphing them to find our vertices and shaded region. Okay, so in case you didn't know, the big goal is to find the min, max, and min of a quantity of some situation. So to do this, we must be able to understand the problem. We can do this by defining our objective. To avoid confusion between our constraints and priorities, we have to make sure our objectives are specific. So now we also have to define our constraints, which are limits to infinite options. Okay, so now that we know what we need to do to understand the problem, we can go into the steps. So step 1, find constraints or limiting equations, or how much decision variables can be. So find constraints or how much decision variables can be. Step 2 is to define our decision variables. Or how much of something. Which, for example, could be if you're trying to define number of books sold to number of movies sold, you could use B for number of books sold and M for number of movies sold. So then step 3 is to write the objective function using the variables. And we want this to be algebraic so that it can minimize the amount. So step 4 is to form the constraints using inequalities and the variables. Step 5 is to add non-negativity constraints, which are kind of equations to kind of form your origin. So it could look like b is greater than 0 or m plus b is less than 50. So now on to step 6, which is to graph all equations and define variables, or to define vertices and the shaded region. Alright, so now moving on to our practice problems. A calculator company produces a scientific calculator and a graphing calculator. Long-term projections indicate an expected demand of at least 100 scientific and 80 graphing calculators each day. Because of limitations on production capacity, no more than 200 scientific and 170 graphing calculators can be made daily. To satisfy a shipping contract, a total of at least 200 calculators must be shipped each day. If each scientific calculator sold results in a $2 loss, but each graphing calculator produces a $5 profit, how many of each type should be made daily to maximize net profits? So, to start this problem off, let's define our constraints, or how much problems. So, looking at our problem, you are going to have x and y, which x is going to be our number of scientific calculators, and y will be our graphing. Okay. So we have to keep in mind, though, the problem says that it has to be at least 100. So we're going to have to change this to at least 100 graphing calculators, scientific calculators, and 80 graphing calculators. So it also tells us the maximum of the shipping contract, which means that we also have no more than 200 scientific and no more than 170 graphing, which leaves us with a minimum of at least 200. So our objective equation is negative 2x plus 5y. So we can simplify some of these equations so that they're easier to graph. And we're going to get P is 2x plus 5y, negative 2x plus 5y. And we can simplify these into x is greater than or equal to 100, but less than or equal to 200, which also means y is greater than or equal to 80, but less than or equal to 170. We can also rewrite this bottom equation to y is greater than or equal to negative x plus 200. So, now that we have all of our equations made, we're going to set up a graph. I'm going to go by 50s on my y-axis, just to make things a little easier. And I'm going to go 50s on my x, so to keep it consistent. So, when we graph these, it's going to look like, so for our x is greater than 100, I'm going to put a line here, but less than 200, put a line there. And so this is my x is less than 200, and this is my x is greater than 100. Now I'm going to graph my y values, which is y is greater than 80 and y is less than 170. So now we got to graph our last equation of y is negative x plus 200. So start at the 200 mark and go down. Going to look like that, which this is y is greater than negative x plus 200. So our corresponding region falls within this area, because that's where all of our lines meet. If we were to test some points, we'd find that that's the region. So our vertices that we get from this is 100, 170, which is right there, 200, 170, which is there, and 280, which is also there, and 120, 80, which is there. And our last point is 100, 100, which is there. So, to find the min and max of this equation, we have to plug our coordinates into our p function. So, I'm gonna make some room. So we have p is negative 2, 100 plus 5, 170. Okay, got them all down. P is also negative 2, 200 plus 5, 170, 200, 580. 2, 120, it's 580, and negative 2, 100, 5, 100. Okay, so you can plug those into a calculator and get them calculated, which is what I'm gonna do. So, gonna have negative 2 and 100 plus 5 and 170, 650, and then 2 and 200, 5 and 170. 450 and 2 and 200, 5 and 80. That's 0. And 2 and 120, 5 and 80 is 160. And finally, and 100 plus 5 and 100 plus 300. So, looking at our values, we can conclude that this is our max, and which means that the solution that we found is they can make 100 scientific and 170 graphing to reach maximum profit. Okay, that's a good example. Let's go to something a little more challenging now. So we have a company makes 2 products, X and Y, using 2 machines, A and B. Each unit of X that is produced requires 50 minutes processing time on machine A and 30 minutes processing time on machine B. Each unit of Y that is produced requires 24 minutes processing time on machine A and 33 minutes processing time on machine B. At the start of the current week, there are 30 units of X and 90 units of Y in stock. Available processing time on machine A is forecast to be 40 hours and on machine B is forecast to be 35 hours. The demand of X in the current week is forecast to be 75 units, and for Y is forecast to be 95 units. Company policy is to maximize the combined sum of the units of X and the units of Y in stock at the end of the week. So, this one's going to be a little more challenging. So, I'm going to start with my variables. So, we'll make it easy. So, X is number of units of X produced. And we'll make Y the number of units of Y produced. So, going off of our word problem, we can find that our constraints are going to be 50, because 50 minutes on the machine and 24 on A. So it has to be less than or equal to machine A time, which is and our next one will be 30 because that's processing time on machine B, which is also 33, which is going to have to be less than or equal to 35. This is machine B. So the number of X units has to be greater than or equal to the forecast of the units, which is 75, minus the beginning that they start with each week. So this makes sure that we are meeting the demand. And so now our units of Y produced has to be the demand, which is 95, minus your initial stock, which is 90. So also that we're meeting the demand. So now our P function, or objective function, is going to be X 30 minus 75, so that we're meeting our demand for there, and Y and 90 minus 95, and this is gonna mean that we want it to look like that. So to simplify it, we'll get X plus Y minus 50. So that we can maximize the number of units left in stock at the end of each week. Okay. And now we're going to graph it. I'm going to go by 5s this time. And 10s on this one. Okay, so now I'm going to graph my functions. So we have Y is greater than 5, so I'm going to put a line there. X is greater than 45, so put a line 45. So X is greater than or equal to 45, and Y is greater than or equal to 5. So now I'm going to graph these functions. So we'll start top. So it's gonna look, so we're just gonna pretend up here is about 2400 because 40 and 60 makes it 24, and gonna graph it. It's gonna go line's a little more visible. And I'm going to graph this one also. Just going to give us about the same thing, but 35 and 60 is about 2100 this time. So I'm going to start about there. Graph that over. So I'm going to label my lines. Okay, so this is a little trickier because my region's just this little triangle down here. Kind of hard to find, but it gives me so I'm gonna have to just go with our vertices of 45, 5, 45, and about 6.25, and 46.5. So now we're going to plug that into our maximum profit. We're going to get P is 45 plus 5 minus 50. P is also 45 plus 6.25 minus 50. And P is I misread my graph. I think it's 45.5 still. 45 minus 50. So I'm going to use a calculator again. Don't drop my whiteboard. We're going to get 45 plus 5 minus 50, 0. 45 plus 6.25 minus 50. And 46 plus 5 minus 50 is 1. So, looking at our variables again, this is our max. So, this means the number of units of X produced is 45 units. And 5 Y units to reach our max 1.25. So that's my more complex example. I hope you have learned something about linear programming and that this video was helpful.